In the previous class, we have discussed about the conduction, and here we are going to start this forced convection. So, or in general convection. So, you see that when we have solved the conduction equation and as a boundary condition of it, we have discussed about the convective heat transport, and that condition we know that it is being referred as Robin's boundary condition. So, in this condition you see that at the solid boundary the conductive transport or conductive heat flux is just equal to the convective flux, and there we have written this convective flux Q is equal to H into Ts minus T infinity, right. So, H we have referred as this Kf by delta, and we have lumped this into the parameter H, and we call it the heat transfer coefficient. This is the heat transfer coefficient, or rather the convective heat transfer coefficient, right. Alternatively, it is also referred as effective film heat transfer coefficient. Now, the major part of this convection actually deals with the finding of H, determination of H, right. So, that we are going to majorly discuss. Now, you see when we start that, before we go into that exact calculations, we must understand that what is basically convection. Convection, you see, it is a mode of heat transport where the net movement of the medium is inevitable. The medium actually moves where or through which the heat is being transported, right. So, it is not a new mechanism altogether, rather we can say that it is a kind of transport or heat energy transfer which is a combination of medium's motion and conduction, right. So, this picture is just like we have small packets of that fluid which is moving around, right, and there is an interface, and from that interface it is taking up the heat through conduction and transporting it to the bulk of the fluid through this motion of that fluid, right. So, convection in general it is a combination of conduction and the motion of the medium, right. Now, if the motion of that medium is caused by some motive device like pump, blower, compressor, fan, etc., it is referred as forced convection, or alternatively, if the motion is caused by density difference, if the motion is caused by density difference and external force field like gravity, then it is natural or free convection, right. So, we have two different types of convections. Like one is the forced convection, another is a natural or free convection, right? Now, as I mentioned that our major target in this entire discussion will be to calculate H, and here we will focus that how to calculate this H. Definitely we will initially try by analytical means, and we will show the limitation of this analytical procedure, and after that we will go for experiments. So, here you see that if I consider an object which has got a surface temperature Ts and we have a free stream of fluid moving over it which has got a temperature T infinity, right. Now, considering a small surface area dA, we can write over here, over this part, the local heat flow rate dQ, which is H into dA into Ts minus T infinity, where T infinity is the free stream temperature, Ts is the surface temperature. So, the total Q we have to integrate, right, over the area A. Right. So, total Q we have to integrate. In order to get this integration being done, we have to know the variation of H, from one point to the other on the surface, on the solid surface, must be known, right. How we know that? We will come to that point. So, Q is this, and if I want to calculate some average heat transfer coefficient, we can write that this is H bar into A into Ts minus T infinity. So, essentially you see that H bar is equal to area averaged value of H, right. Now, the point is that how to get this distribution of H. So, we have to solve actually if I choose the coordinate as say x, y, z, right. So, at each and every point in the bulk of the fluid, I must know this T, x, y, z, and this is the normal direction. So, you see that H, how we can solve H? If I know the temperature field of this fluid, then we can write that minus of Kf del T del N, N is this normal direction, right. So, at this area A must be is equal to H into Ts minus T infinity. So, this is very important equation, though in a not in a working form, it is more a qualitative equation, right. So, N represents the normal direction. So, at this point the conductive transport must be is equal to the convective transport. S is the solid surface temperature, which we are assuming to be uniform. T infinity is the bulk liquid temperature. So, if I can solve this temperature field, I definitely can find out this gradient, and from there I can get the value of H, right, which is to be integrated over this area in order to get this average H value. Now, this is not a typical working equation. Actually, next we have to go for this working equation where the geometry is very well defined. So, the simplest geometry you see, the simplest geometry is the flow over a flat plate, right. So, here we fix our coordinate system, this is y and this is x, and we have the free stream capital U, its temperature is T infinity. Now, before we go into the discussion, here it is very important to understand that what is thermal boundary layer. So, what is thermal boundary layer? Let us say the plate temperature is Ts. So, at any point at any x, we have a temperature profile like this, where this much here it's T infinity, right? And as we go on for a higher value of x and draw the similar profile, what is expected? Definitely this, just like the boundary layer thickness, here it will be delta T, the thermal boundary layer thickness, that will definitely increase because the thermal front will penetrate more and more into that fluid, right? The thermal front will penetrate more and more into that fluid, so this delta value will increase, so it will be something like this, right? So this value is same, this is Ts again. Now if I join, this is say this is delta T1 and this is delta T2, right? Now if I join these points, if I am joining these points, what will happen? I will get, just similar to hydrodynamics, I will get a boundary layer, right? So inside the boundary layer, so boundary layer thickness, this is delta T. So you can say that delta T is a function of x, and for y less than delta T, del T del y is not equal to 0, and for y greater than delta T, del T del y is equal to 0, right? So that's the precise quantitative description of this boundary layer thickness. And you see what happens, just like thermal, this hydrodynamic boundary layer, the thermal boundary layer also grows with x. So basically we can say that here this d delta T dx is positive, right? So that much we can infer about this thermal boundary layer, its profile, temperature profile, and how it is being defined. Now you see this boundary layer thickness, actually it represents the penetration of this thermal front, that how far this different thermal state is penetrating into that fluid, because the plate is basically having a different thermal state than that of the bulk fluid. The plate temperature is Ts and the free stream temperature is T infinity, and let us say this Ts is greater than T infinity. So obviously there will be heat flow into that fluid, and as a consequence the temperature close to the plate will be higher, and as we move far into the deep into that fluid, definitely it will be at some point of time it will acquire the same temperature as that of T infinity, right? So its temperature will be T infinity once again after a certain distance. So that distance is basically the thermal boundary layer thickness, okay? So y less than delta T, we have del T del y equal to, not equal to 0, and y greater than delta T, it must be del T del y is equal to 0, right? So you see that if I can solve for the temperature profile, if T as a function of x comma y under steady state is known, then we can write h, now it is a function of x, right, into Ts minus T infinity is equal to minus of kf del T del y at y equal to 0. Now it is much well defined. Instead of n, now we have a chosen direction, and that direction matches with one of the original coordinate axis, and we can write that Hx, that local heat transfer coefficient, this is the heat transfer coefficient at x, right? So that multiplied by Ts minus T infinity is equal to minus of Kf, Kf is the thermal conductivity of the fluid, into del T del y at y is equal to 0. Now you see there is a typical inference we can actually we can put forward here, that del T del y here, it will be obviously lower. Why? Because at x is equal to x1, this del T del y at y is equal to 0 is in the order of Ts minus T infinity by delta T1, and x is equal to x2, del t del y at y is equal to 0 is in the order of Ts minus T infinity divided by delta T2. So, del t del y is equal to 0 at x2 is lower than del t del y is equal to 0 at x1. And you see this Hx is proportional to del t del y, right? Here, from here we can write this Hx is proportional to this minus of del t del y at y is equal to 0. So, basically it will be this minus, right? So, its minus is definitely this is also minus, because in the y direction the temperature actually decreases. So, it will be Ts minus T infinity. So, what we can say that Hx at this 1 is greater than Hx at 2, right? And one of the very important consequence, though it is important for the mathematical standpoint, it's not important from the engineering standpoint. At this point where delta is equal to 0, Hx is actually infinity. So, at x is equal to 0, right, Hx tends to infinity. So, this is more a point of interest for the mathematicians, right, but as it is a point we are not interested about it, we have to go for averaging this heat transfer coefficient over this entire length of the plate. Okay. So, what we have got, that if I have to calculate the local heat transfer coefficient, mostly I have to solve for the temperature distribution surrounding this solid object, right. Here also we have to know this temperature distribution T as a function of x and y. So, once we know this T as a function of x and y, then and then only we can solve for this heat transfer coefficient, otherwise it is not possible. So, if I have to solve for the temperature field, what will be my governing equation? Just like in fluid mechanics we have seen, whenever we are trying to solve this velocity field, we majorly used either shell balance, or in a generalized form there was Navier-Stokes equation. So, here we must solve for a general energy equation, or must get some general energy equation, right, like very similar to Navier-Stokes equation, and solving that we should get this temperature field, right. So, before going into that derivations of general energy equation, it is important to understand some of the significance of some of the representation of some of these parameters, like heat transfer coefficient, like these thermal diffusivities, and at the same time the velocity, because the temperature field, as I mentioned, the convection is a combination of conduction and liquids, or the fluid is in motion, right. So, there you must know that the velocity must be an important parameter. So, velocity is highly a deterministic factor in this entire distribution of thermal temperature field. So, the point is here, before we go for solving or deriving this general energy equation, we must know some of the important way of representing these three major variables. What are they? One is heat transfer coefficient, second one definitely the velocity, third one is the diffusivities, right. It may be a momentum diffusivity, it may be thermal diffusivity. So, you see the first number is Nusselt number, right. So, Nusselt number Nu, this is defined as HL by K. You see, this is the characteristic dimension of the system and K is the thermal conductivity of fluid. That is the difference. Remember that if we change it to the thermal conductivity of solid, it becomes Biot number. So, Nusselt number is primarily different from Biot number in a sense that it uses K of fluid, right. So, what is the physical significance of Nusselt number? Just like here it is the general definition. See, for the flat plate, we can define the Nusselt number, average Nusselt number, as h bar into L by K, where L is the length of the plate, right. This is the average Nusselt number. Or NUX, that is the local Nusselt number. And that is Hx into x divided by K. So, the significance of the Nusselt number we can actually get from this equating relation. Like Hx, we can write Ts minus T infinity is equal to minus of Kf del T del y at y is equal to 0. Now, you see that Hx divided by Kf, we can write minus of del T del y at y is equal to 0 divided by Ts minus T infinity, Ts minus T infinity. Now, if I divide it by delta T, right. Here I am writing delta T, where delta T is the thickness of thermal boundary layer. So, this can be further written as minus of del T del y at y is equal to 0 divided by Ts minus T infinity divided by delta T into L, right. Why? Because as this delta T is in the order of L. Okay. So, delta T is in the order of L. So, here from we can write that Hx into L divided by K or Kf, whatever, this is minus of del T del y at y is equal to 0 divided by Ts minus T infinity divided by delta T, right. So, what is the physical meaning of this ratio? This represents wall temperature gradient divided by temperature gradient existing across or existing in the fluid over the thermal boundary layer, right. So, wall temperature gradient divided by the temperature gradient existing over the fluid over the thermal, or existing in the fluid over the thermal boundary layer, or temperature gradient existing from the plate to the bulk of the fluid, something like that. So, this is basically the Nusselt number, right. Okay. So, the thing is, next is something related to diffusivity, and that we are discussing here. What is that? Prandtl number, PR, which is Cp mu by K. So, that is, we can write C mu divided by rho, K divided by rho Cp. So, it is nu divided by alpha, right. A ratio of momentum diffusivity divided by thermal diffusivity, right. So, what is the significance of it? You see, that in this conduction, in the chapter of conduction, where we have studied heat transfer in semi-infinite, solid rod, right, where we have used the similarity solution technique, right. There we have seen that penetration, this was what? Thermal penetration. We have seen that this is proportional to under root of alpha into T. There was some constant, right. Actually, you see, the thermal boundary layer or hydrodynamic boundary layer, the respective thickness, basically it's a measure of that same penetration, right. So, and the penetration will be high if I have, here it's obvious from this typical example of semi-infinite solid rod, the penetration will be high if I am having corresponding higher diffusivity. So, delta, that is hydrodynamic boundary layer thickness, will be definitely in the order of, or it will increase, right. It will increase, or rather we can write, okay, it is better to be written in terms of in the order of. So, it is in the order of nu, because more is the nu, higher will be this delta. Exactly I am not writing whether it is root or this whether it is root or to the power half or 1/3, whatever, I am not writing it. I am simply going for an order analysis. And delta T, the thermal boundary layer thickness, right, is in the order of alpha. So, obviously from here delta by delta T must be in the order of nu divided by alpha, and that is equal to Prandtl number. So, we have to note that delta by delta T, it's in the order of Prandtl number, and we will see later that this is actually proportional to Prandtl number to the power 1/3, right. So, here generally we can say that whenever Prandtl number is greater than 1, delta is greater than delta T. Prandtl number, if it is less than 1, delta is less than delta T. And if you see the scale of Prandtl number, right, the scale of Prandtl number, here 10 to the power 0, it will be this water, right. So, let me just check what is the exact this value. Yeah, 10 to the power 0 to this 10 to the power, say 10 to the power 1, next we have 10 to the power 2, 10 to the power 3, and on this side 10 to the power minus 1, 10 to the power minus 2, right. So, water will be here from 1 to this around Prandtl number for water is actually this around 10, right, but that depends on temperature. So, it will be ranging here. Next, for light organic, we will go for this region. So, this is light organic. And long chain organics, you see, that will be oils. And on the other hand, from 10 to the power minus 1 to 1, we have gases, and this region is for liquid metal like mercury. Because for liquid metal, you see that K value is pretty high. Cp mu by K, the K value is pretty high. So, we will have extremely small Prandtl number for liquid metal. Now, for air, the Prandtl number is 0.7, right. 7 for water at room temperature, oils have very high Prandtl number, liquid metal has got very low Prandtl number. So, this variation is because of the difference in temperature. So, first we have discussed about the representation of this heat transfer coefficient in the dimensionless form, that is Nusselt number, the ratio of the diffusivity in terms of the Prandtl number, and the third one, as I have mentioned, the velocity. I am not discussing it. So, definitely you can understand that it will be the Reynolds number, right? Reynolds number definition is very well known, so I am not going into that. So with that, knowing these sort of representations and the respective dimensionless groups, let us now proceed to the formulation of energy equation. See, again we will consider this is not a generalized derivation. We are not going to consider this this three-dimensional, this shell of this dx, dy and dz with sides. We are not going to discuss that. We will consider a simple case, right? Because the energy equation structurally it's much more complicated. So, and in undergrad level, we need mostly the form of this general energy equation for simple systems like flow over flat plate or flow in a cylindrical tube. So, what we are trying to do to avoid the complexity of derivation, we choose this simple example of flow over a flat plate, right. So, in a flow over a flat plate, why we are choosing it? Because it is two-dimensional. The flow is two-dimensional, right. We could have used this three-dimensional flow where we will have this x, y, z, these three variations, and our shell, this differential control volume will be of the size dx, dy and dz. These sides will be the dx, dy and dz. Here we are not going to do that because that will make this entire analysis quite complicated. So, we choose a two-dimensional special flow, that is a flow over about this flat plate, and here the control volume of the shell will be two-dimensional. So, this is energy equation for flow over a flat plate. Energy equation for flow over a flat plate. So, we choose this geometry, it is very well known, as you all know, y and x. This is the thermal boundary layer and thermal boundary layer, right, and we are choosing this as control volume. So, this is dx and this much is dy. So, first before the derivation, let us write down the assumptions. The flow is 2D, steady, incompressible, and laminar, right. Second, the fluid properties remaining constant. That is fluid properties. What are the fluid properties? Mu, rho, Cp, K, etc. These are remaining constant, right. Next, kinetic energy in y direction is negligible relative to kinetic energy in x direction. Fourth, it is an open flow, so there is no pressure gradient, del P del x and del P del y both are equal to 0. Fifth, this Prandtl number is, let us say, greater than actually this value is 0.7, though see I have mentioned that Prandtl number greater than 1, delta is greater than delta t, but actually the value is not exactly 1, it is lower than 1, right, for most of the fluid. So, if Prandtl number is greater than 0.7, so that delta t is smaller than delta, right. Sixth, viscous dissipation. This I am not going to explain just right now, definitely through the course of derivation I will explain it. Viscous dissipation in y direction is negligible. So actually the viscous dissipation, you see that when we are dealing with this general energy equation, right, which will include the conduction term, convection term, right, then unsteady state term, here we are not going to use this unsteady state term, then there may be heat generation, right, because the fluid is working against friction, and friction is a non-conservative force field. So any work against any non-conservative force field finally appears into thermal energy. So that is definitely going to change the temperature or the thermal state of that system. Okay? So that's the process of this energy generation because of work being done against friction is called viscous dissipation. Okay? So that's the more or less these assumptions here. Right. So now over this specific shell, we will consider the different energy inflow and outflow, and under steady state there is no energy accumulation. So we have to write the different inflow and outflow terms, and finally we have to cancel it. So you see that what are the terms? Right. In this direction, this is say dx, this is dy. So here in this direction, we will have I will be basically rho Cp, right. So rho Cp is what? Rho Cp is the or rather Cpt, not rho Cp, it's Cpt. It is the enthalpy per unit mass. So this is, we will consider as thermal energy per unit mass, okay, I. And what are the other forms of energy? Definitely it is the kinetic energy, right, because from here to here or from here to here the potential energy change is negligibly small, and we have neglected the kinetic energy in y direction, right. So the kinetic energy term is only u square by 2 per unit mass. So that is to be multiplied by mass flow rate. So it is rho into u into area. Area will be dy into w, right, where w is the width of the plate. And actually this control volume stretched over this entire width of the plate. So on this side, it will be rho into u into I plus u square by 2 dy into w plus del x of rho into u into I plus u square by 2 dy into w, right, into dx. Okay. This is typically the Taylor series expansion. So here, what are the terms? First, we will definitely have Qy, the conductive. Okay, there is another assumption. Conductive transport in x direction is negligible compared to transport because of bulk flow. See, the flow is basically horizontal. So if in the x direction the conductive transport must be negligible compared to this convective or the bulk flow based transport of energy, right. So this is conductive heat flux. So that multiplied by w into dx. So here we will have Qy plus del Qy del y into dy whole bracket w into dx. Additionally, we will have the same sort of this thermal plus kinetic u square by 2 rho into V into dx into W, and that's the beauty of energy transport. See, what is very important, this is the energy. You may be thinking that why in this y direction I am having u square, but once it is u square, it is energy, right? So this is the energy, thermal energy plus kinetic energy of the fluid, right, which may be transported in the y direction, and the velocity is v. So this rho into v into dx into w is the mass flow rate multiplied by energy per unit mass, and that energy is consisting, the kinetic energy part is only consisting of x directional velocity, not y directional velocity according to our assumption. But that does not mean there will be no contribution or no energy flow of this x directional kinetic energy along y direction. Okay. So here it will be rho into V I plus u square by 2 plus del y of rho into V I plus u square by 2, this whole bracket into W dx. Next, and here comes the viscous dissipation term. Now you see, in order to explain it, on this shell I have two shear stresses. Here this tau, these are all this tau yx type, the value may change, right. This is tau yx type, and here this is tau xy type. And we know that tau yx and tau xy are same. Okay. Now again, the force into velocity is equal to the work, right. Now if I am thinking, or this energy is equal to the force into work. So how much energy, because to overcome this shear stress, is basically invested, right. So you see that actually if I multiply tau yx into corresponding velocity, or here tau xy into corresponding velocity, I must get that term. Why? Because this is force per unit area, and here it is length per unit, this is velocity, right, this is velocity. So this will be force into velocity is equal to the power per unit area. Okay. The flow rate, energy flow rate per unit time. So it is basically energy flux. Right. And that energy flux is the flux of viscous dissipation, energy flux due to viscous dissipation. Now we have to note that u, tau xy and tau yx both are same. We have seen it in the symmetric property of the stress tensor. However, u is much higher than v. So for a simple analysis, tau yx into u and tau xy into v, so we can say that this is much higher than tau xy into v. So simply we drop this term, right. And this is a kind of energy, or this is a work rather, it's not a material flow type. This is material flow type, this is also material flow type, but this is conduction, is a energy transport, right. So energy transport as it is. So this is basically the heat term, and additionally we have a work term, right. So if it is a work term, this work is being performed by the surrounding on the system, so there will be a minus sign, right. So this transforms the energy flux into with the appropriate sign, because truly we have to use this steady flow energy equation for an integral control volume. Here we are not going to do that. Here we simply write that all energy fluxes will be equal to 0, but that we cannot write. Why we cannot write that? Because you see q dot minus w dot, q dot for this control volume analysis, q dot minus w dot is equal to the steady flow energy equation whatever we have derived. It's the summation of h plus v square by 2 plus gz into m dot. and this terms, I mean the summation, the terms will be positive if it is an outflow, terms will be negative if it is an inflow, right. So, outflow minus inflow term, this right hand side is outflow minus inflow term, right. And you see, just let me write, Q dot minus W dot is equal to this this H plus Z into m dot out minus H plus V square by 2 plus GZ m dot in, right. So, if I am trying to write this Q dot, W dot is what? If it is it's positive if work being done by the system. This is positive if heat is given to the system. So, in the sense QY and this QY, we do not have to go for any sign change, okay. It is heat given to the system. However, this W dot is positive, W dot is positive if the work is being performed by the system, right. If it is the work being performed by the system, and that is why we have to change the sign, unlike here. So, here the term will be minus of u tau yx plus del del y of u tau yx dy into w dx. Now, we will write the sum of all the terms to be equal to 0. So, this minus this or out minus in del del y of rho u I plus u square by 2 into w dx dy, right, plus here out minus in del qy del y into w into dy into dx, right. Next here, so this derivative term del, sorry, here it will be del del x, right, del del x, okay, here it will be del del x, and for this y directional term it will be del del y rho into v I plus u square by 2 whole bracket w into dx into dy. Now, for viscous dissipation the term is plus del del y, and here I missed the minus sign, this minus. So, minus of u tau yx into w into dx into dy, that will be equal to 0. So, overall the x directional total transport, energy transport, y directional transport, y directional conduction of heat, and x directional. This why it is being referred as x directional viscous dissipation, because the respective shear stress, its force direction is x direction, and that is why in the assumption we have mentioned that we are neglecting the viscous dissipation in the y direction. Actually, there is no direction of viscous dissipation because it is energy term. However, you have to understand that whenever I am saying that x component or y component of viscous dissipation, actually we are referring back to the respective shear stress, the force direction of the respective shear stress. Here the shear stress for this tau yx is x directional, right, and that we are considering. However, y directional force, that is tau xy, the respective viscous dissipation we are neglecting, right. So, that is the justification of assumption. So, here you see what will happen, this w dx dy first we can drop, and here rho into I plus u square by 2, there are two derivatives, one is with respect to u, another is with respect to this term, and here this term with u derivative will be u del x, and here the v's derivative will be del v del y, right. So that's one first term. Next, so this is equal to 0 from continuity. Continuity equation for two-dimensional incompressible flow will assume this form. Next, plus rho u into del I del x, right, plus rho v del I del y, plus here, plus rho u into del x of u square by 2, del x of u square by 2. So it is u du. So it is u into del u del x, plus here rho v into u del u del y, right. Next here, let's substitute this qy. Here qy will be is equal to minus of k into del t del y according to Fourier's law, because we have neglected the conduction in x direction. So this term will be minus of k del square t del y square, and here what will be the term? You are using Newtonian fluid, so del del y will be minus of u mu into del u del y, and that's the entire thing is equal to 0. Okay. So further, this plus, yes. So this term, first term cancels out. So next here we can write rho this Cp, if I split I now, u into del t del x plus v into del t del y, u into del t del x plus v into del t del y, plus you see that we can write u, if I take this u common, then rho within bracket u del u del x plus v del u del y, right. And here we will have a pure second order derivative. See, this term will be minus of mu u into del square u del y square. So if I write that taking u common, minus of mu del square u del y square, right. Then minus del square t k into del square t del y square, and minus of mu del u del y whole square, that's equal to 0. So what is very important to note that boundary layer Navier-Stokes equation for x direction is nothing but this, and the entire term will be equal to 0, as Navier-Stokes equation for Navier-Stokes equation x direction for boundary layer is u del u del x plus v del u del y is equal to nu del square u del y square. So from there this entire third bracket term becomes 0. The simple final form of this energy equation, specifically this is not a general one, we are getting a restricted form for this boundary layer flow, right. And what is that form? The form is rho Cp u del t del x v del t del y is equal to k into del square t del y square plus mu del u del y whole square, right. So this is the convection term, this is the conduction term, and this is the viscous dissipation term. Now if I just this is not a derivation. In the next what we are going to do, we can have an analogy that this is the u del t del x, v del t del y, and if I add z direction, it will be w del t del z, right? And if we add unsteady state, there will be del t, because it's having a quite similarity with the Navier-Stokes equation. So here we are going for generalization, though it is not logical, it's more intuitive. So rho Cp here we can write del t plus u del t del x plus v del t del y plus w del t del z is equal to. Now here if I have these three directions, so we have solved it for conduction. We can have heat generation, so it will be Q. So let's have heat generation per unit volume, right? However, the last term cannot be just, we cannot directly write. I know the form, I am writing the term for viscous dissipation. Just you remember or note that, but more precisely you remember the form which is for this boundary layer flow. And the term is, you see, 2 mu d double dot d, where d, we have defined it actually, it is grad V plus grad V transpose by 2, right? And the double dot gives you a scalar product, we know from this tensor algebra. So this is viscous dissipation. Definitely it is difficult to evaluate for complex system or in the general form. So that's why it is in a compact form, it is in the vector in this general representation. Actually the equation is scalar equation. So that can be expressed in this form. Okay. So our final equation is rho Cp material derivative capital ddt is equal to k grad square T plus Q plus 2 mu d double dot d. For Newtonian fluid, we have the general energy equation, right? General energy equation for Newtonian fluid, right? Now in most of the cases, what happens that this viscous dissipation term is negligibly small compared to this conduction and convection term. Okay. So that we can establish from here. You see, this we can write u del t del x v del t del y is equal to k divided by rho Cp del square t del y square plus mu divided by rho Cp into del u del y whole square. Okay. Now mu divided by or mu into del u del y whole square divided by k into del t del y or del square t del y square, this will be mu into u infinity by delta whole square, and here k into Ts minus T infinity by delta square. Now I am not actually differentiating the thermal boundary layer and this hydrodynamic boundary layer. What I am writing here, it's just like that they delta T and delta will be in the order of each other. Delta T is in the order of delta. Okay. Considering that, if I write, I will get this. Okay. So that's equal to mu into u infinity square divided by k into Ts minus T infinity. Mu into u infinity square divided by k into Ts minus T infinity. and that's equal to further Cp mu by K into U infinity square divided by Cp into Ts minus T infinity. Definitely this first term is Prandtl number and the second is called Eckert number. The second group, that is U infinity square divided by Cp into T minus T infinity, that's called the Eckert number. Yeah. This Eckert number, you see, what will be the significance? The significance is the kinetic energy. Basically, we can write this like kinetic energy per unit mass of the free stream divided by thermal energy per unit mass of the plate relative to this relative to free stream temperature, right. Some sort of this we can explain as this physical significance of Eckert number. So, if Prandtl number into Eckert number is much less than 1, we can neglect viscous dissipation term. Right. You see, in 2007 there was a great question like write the general energy equation for or the energy equation for fully developed laminar flow in a pipe. Just try to understand. I will post this question that try to develop this energy equation for laminar flow through a pipe which is fully developed and the wall of the pipe is being maintained at constant temperature. So, what will be the equation and what will be the boundary conditions? Right. So, equation, you see V here will be 0 0 Vz only x directional flow or z directional flow in a pipe, right. So, and steady state laminar fully developed flow. So, what we will have? Rho Cp del T, that term will be 0 and here V dot grad T, this term will reduce to Vz into del T del Z only because Vr is 0, V theta is 0. Here the conduction term we can have it in the r direction. So, 1 by r del r of r del T del r. In theta there will be no variation, so we write directly del square T del Z square. No heat generation as well, no heat generation. Q0 plus 2 mu d double dot d, that's also 0 because there is no viscous dissipation. So, my final equation reduces to, you see, the final form of this equation reduces to this rho Cp and Vz. Vz is what? U into 1 minus small r square by capital R square. That's also dependent. Del T del Z is equal to, and here K rho Cp, here K divided by rho Cp, it's alpha into 1 by r del r of r del T del r plus del square T del Z square. So, that's the final equation. And what will be the boundary condition? Here r is equal to 0. It is a case of axis symmetry. So del T del r is equal to 0, the first one. Second boundary condition, say at r is equal to capital R, I have mentioned that wall is maintained at constant temperature, Tw. And third condition, because we have Z, right? Z and Z square. So if the pipe is something like this, and at this pipe inlet, let's say the temperature of the fluid is T0. So you can write at Z is equal to 0, T is equal to T0. And here we have this heating, right? The pipe temperature is different from this pipe temperature is different from the fluid temperature. But from here, if the pipe is insulated, definitely that should be given. There is no further change of this temperature profile over this section. So, and that section, if it is Z is equal to L, we can write that for Z is equal to L, del T del Z is equal to 0, and which gives that there is no further change of temperature, right? But generally the pipe wall temperature constant is not a given standard condition. What is given? I have a heater, so it's giving you a heat flux Q, right? Newman type condition, okay? So we can write there this Q is equal to K into del T del R. Why K? Because this is a direction of negative R. This is negative R direction. So we will write that Q is heat given, and in this direction the heat flux is minus del K del T del R. Like if I write the heat flow in this direction, what will be that? Minus of K del T del R, right? So minus of K del T del R plus of Q equal to 0. So Q is naturally K into del T del R at R is equal to capital R. And the Q, this value is given like 500 watt per meter square or something like that, right? So it is given. So with that we can solve this problem. So you see that again, if we go back to boundary layer, if we go back to boundary layer, we have the energy equation. So what are the conditions? Steady state we have assumed, and we also assume no viscous dissipation. And all the previous assumptions, steady state already we have assumed. So no viscous dissipation. Under this condition, the equation changes to U del T del X plus V del T del Y is equal to K by rho Cp. So it's alpha del square T del Y square. Now how to solve U and V? Again we have to write continuity. Del U del X plus del V del Y equal to 0, and finally this Navier-Stokes that U del U del X plus V del U del Y is equal to nu del square U del Y square, right? So these three equations are to be simultaneously solved for three variable U, V and T. And you see the boundary condition, X is equal to 0, T is equal to T infinity and U is equal to U infinity. V is equal to 0. Y is equal to 0, T is equal to Ts, U is equal to V equal to 0. Y tending to infinity, T is equal to T infinity, U is equal to U infinity, or alternatively we can write that del U del Y is equal to del T del Y is equal to 0 and V is equal to 0, right? So with that, if I solve, we can get actually this T as a function of X, Y, R. Because if we just remember our original objective, we have to solve for the temperature field. Next we apply the boundary condition that H into Ts minus T infinity is equal to minus of Kf into del T del Y at Y is equal to 0, right? From there we can solve for Hx. So that you can understand, it's quite complicated. It has been solved by a similarity solution technique. We are not going into that. Just like in boundary layer, where we have considered only those two equations, we have said that it was Blasius solution, right? But alternative to Blasius, there was something called one carbon momentum integral equation. So similarly here, alternative to the solution of this complex mathematical structure, so alternative here is one carbon energy integral equation. Right? And that we are going to discuss in the next session.